We last left off with, what was the last thing we did? I'm confusing this with 251.
We did this,
And then we did hangman.
and then this is what we just.
I did the colliding thing.
Pardon?
We just started talking about the colliding.
Okay.
Kepler's law.
All right, so let's start out with this idea of force and displacement. That's in the next chapters. Force and time will show up after that.
So then we're still in chapter 6.
No, this is chapter 7.
So,
Work equals force times displacement. And when I do my multiplication, it is a dot. It has to be a dot, because this is known as a dot product. I think we've talked about dot products before.
just a wee bit.
What does anyone remember about dot products? What is the wee bit we talked about before?
It was some, but it was displacement,
It was something.
dot acceleration.
It
That
was
was one.
when you multiplied vectors. I remember that.
Okay, it is vector multiplication. What's the other type of vector multiplication that's not dot product?
I think I'm remembering that we had like two sets of numbers in parentheses. I could be totally, am I totally wrong about this?
Two sets of numbers in parentheses. That sounds like polar notation for a vector.
Yeah.
All right, the other way of multiplying is known as a cross product. So let's talk about the dot product versus the cross product as sort of a refresher, since people were not forthcoming with the big differences here. All right, so dot product, also known as a scalar product. And then parenthetically, I'll just make the notation inner product. That's something when you get into Calc 3, I think inner product will show up. Why do you suppose it's called dot product?
Because it's a dot, and you're getting multiplication from it.
And why is it called a scalar product?
Because it's multiplying the magnitudes.
Well, there's multiplying the magnitudes over there too.
Now this might be completely off the wall, but if you're multiplying two vectors cancel out.
Not in the sense that most people usually talk about vectors canceling out.
Yeah.
All right, so notice there's no symbol right here over the W. Why would you guess it's called scalar product?
You're finding a non-vector, like
Yeah.
a number.
The answer is a scalar. All right, and over here, this is known as a cross product because of the symbol. Also known as a vector product.
And an outer product.
Yep. All right, why do you suppose that's called a vector product?
Because your resultant is a vector.
As far as we're concerned, yeah. It actually produces what's called an axial vector or a pseudo vector. I think axial vector is the more current term. But as far as we're concerned, there is no situation where the difference between an axial vector and a regular vector, there's no point in which the difference makes any difference. So we can treat it like a vector. Matter of fact, there was no situation in my PhD work where I cared the difference. So, but there's a subtle difference that theorists care about. Deals with reflection.
Like flat earthers or?
You said theorists, and I think that's what-
Theorists, like, what do you think I said?
No, I was like
That's what led him
theorists,
to that.
like flat earthers.
Okay,
We,
no, these are not like flat earthers, these are
Moving on.
I was trying to do a comparison, like people care about the Oxford comma or not, like, no, I care about the Oxford comma. The people who are even more pedantic than I am. All right, so when you're doing a dot product, you get a scalar. So if I'm multiplying two vectors here, so cleverly called vector A and vector B. Obviously, they each have a magnitude, but how do I deal with direction? Well, if we break A up into components, perpendicular components, where one component is along the direction of B and one of them is perpendicular to B. So I'm just going to call this A parallel and A perpendicular. When you're doing a dot product, you're multiplying the parallel parts. So A dot B is going to be A parallel times B. And it turns out, well, this angle here is theta, or which I'm going to call it theta. So with that angle right there, I know that A parallel is just the magnitude of A times the cosine of theta. So this is just A cosine theta B, cosine theta, or AB cosine theta. Which means I could have broken B up into its components. So if I go back to what I had before, where I had A going this way and B going that way, if I broke B up instead of A, I got part parallel, part perpendicular, where this is B parallel and B perpendicular, and that's theta. That's B cosine of theta. And you end up with the exact same thing. So it doesn't matter which one you break up, you're just going to multiply the parallel parts. So therefore, commutative property holds. That would be the same as B dot A. So it doesn't matter the order in which you multiply. Unlike cross products, it doesn't matter the order. So if A is a vector 4 newtons 30 degrees and B is 5 meters 70 degrees, what would A dot B be?
How do you have newtons and meters?
Pardon?
How would you have newtons and meters?
You just multiply.
So
So you'll have
meters
meters.
per
Yes.
newtons per meter?
Not per. Per is a division. You're
Newton
multiplying.
meters.
It'd be a newton meter.
Not newton.
But physicists in this context, that's too much to say, so they have another word for it. We'll get to that in a moment. So, the dot product,
So you'll have
I wanna say 20.
20 newton meters.
times,
210 degrees?
no, that doesn't work out that, like that.
Really?
Times the, don't forget, you're gonna ultimately end up with a scalar, so having 210 degrees would not work particularly well, or it'd be 2100 actually, but.
Yeah.
Cosine of the angle between them. What is the angle between them?
Is it, oh, no.
60?
5.
No, not 5.
5.
Is it 80?
No, it'd be,
All right, 30 degrees,
yeah.
let's say 30 degrees, 70 degrees. The angle between 70 and 30.
50, sorry.
Try that one again.
40.
40, yes, thank you.
So you just subtract.
Yeah, just subtract them.
Okay.
And if the question is which one do we subtract from which, it doesn't matter because
It has to be positive.
cosine of theta is equal to the cosine of negative theta. This is known as an even function. It doesn't matter which one you subtract from which. So times the cosine of 40 degrees. So it's the magnitude of one times the magnitude of the other times the cosine of the angle between them. And you get, just for completeness here, Gilbert? What is it?
It is. So I just did 20 cosine 40,
Yeah.
and it'll be 15.32.
Whew. Not bad.
Literally, but it's a 15.321, not.
Yeah, okay, I was
Okay.
off my fifth significant figure.
And it'll be Newton meters.
Yeah. Now, when you write Newton meters, please put a dot in between. Now, if you put capital N first, and then meters, capital N it's not a prefix for anything. This would be understood. Out of habit, I recommend putting the dot in between it. Now, if you wanted to write meter newtons, which is also acceptable, you definitely have to put the dot in between it, because that's a meter newton.
That's a millinano.
Yes.
Right, millinano, that was it.
Nano's a lowercase n.
Oh.
All right, now I alluded earlier to within context, so let's actually give a context there. So I have an object that is going to have a displacement of 5 meters at 70 degrees, so it's going to go 5 meters, angle of 70 degrees. And as it moves, I'm going to be pushing on it with a force of 4 newtons at an angle of 30 degrees, or pulling, whichever way it goes. So there's a force here of 30 degrees and 4 newtons. Well, I would expect this object is going to speed up, because part of my pull is in the direction of motion. Now, why it doesn't go in that direction, it doesn't really matter. It could have already been moving in that, and then I applied a force to it. I guess something like that, and then I applied a force to it. So in that context here, we're talking about the work done, about what is the result of my applying a force to an object that's moving. The units would be joules. So that problem over there, 15.321 Newton meters in this context is equal to 15.321 joules, capital J.
Does that work for most vectors, or is it just the specific vector that we use joules?
If you're talking about a force being applied to an object that has a displacement, it's going to be joules. If you're dealing with newtons and meters, it's joules.
Is that an N in front of what's supposed to be a J?
The-
He
what
just
here?
spelled out units, I believe.
Oh, there we go.
Anyone want to take a wild shot about who was named after?
Joule.
Julius Caesar?
Oh, yes. Yes, yes.
Obviously.
No one has speculated that one before, but I'm gonna just on the limb say no, but who knows?
Darn, it was close.
It was named after the chain refreshment establishment of Orange Julius.
I was close.
What if capitalism got into unit naming? This is called the McDonald's. All right, do one other dot product here. So let's say that the force I'm applying to this object is 5 newtons I hat plus 3 newtons J hat, and my displacement is -2 meters. Actually, I'm going to write it slightly differently. -2 I hat plus 4 J hat meters. And this marker just is making me sad. Again, you're multiplying parallel components. So I want to take a shot at what the dot product would be. Hence, you do not have to put it into polar notation first.
So you're gonna have. You're gonna have, -10 Newton Newton meters. Plus 12 Newton meters. But I feel like we have to have an I hat and a J hat somewhere.
Well, I think, my thinking was, it's like a, I was gonna say it's like a coordinate, and like the first one would be X, which would be the, but it's,
I mean, if you think of it in coordinates, you're multiplying the X coordinates, and you're multiplying the Y coordinates and add them. So the final answer,
2 Newton meters. Oh, 2 joules.
Newton meters is fine, it's not wrong. Didn't feel like writing it. Do you want to point out one thing of the notation, the fact that I either put the unit next to both numbers, or I put parentheses around it if I just want to write the units once.
what is a joule?
What is a joule?
Yeah.
Besides a Newton meter?
Well,
It's the amount of work it takes in order to, the minimum amount of work it takes in order to move an object 1 meter applying a 1 Newton force.
so it's like
Do you want to, there are a couple ways of answering it besides the smart ass way I just did. What are you looking for?
I was just curious, cause, I think of, like, just energy when I do that word, but I could be totally wrong.
No, you're not. So let's actually connect it. Since he's now said the magic E word there, let's somehow figure out a connection between work and energy. All right, so what I want to look here is the total work that is done on an object. Well, if I'm finding the total work, I'm looking at the total force. So this would be the force total. Dot delta X, R, S, whatever letter you happen to be using for position. And based upon Newton's second law, what's the total force equal to? Or to what is the total force equal?
the opposite force. Never mind.
Mass times acceleration.
That's the one. So this is equal to mass times acceleration. And what's the math definition of acceleration?
Change in velocity over the change in time.
Okay, so that's mass times change in velocity over the change in time. And trying to find displacement, we got two cape form. We're assuming constant acceleration for the derivation. It also works if acceleration is not constant. What is the displacement formula? The cape displacement formula, which has both velocities in it.
Oh. Initial velocity. Time. No. Initial velocity time.
Plus.
Oh. Yep. Okay. Initial velocity plus final velocity over 2.
Yeah, you're finding an average times
Times time.
All right. Well, the dividing by 2, that's just like multiplying by a half. That is multiplying by a half, so I'm just going to factor that out. My delta t's cancel out. So what this now is reduced to is 1/2 times the mass times v final minus v initial dot. I'm just going to reverse the order of my addition there. V final plus V initial. And so now I'm doing a dot product. Well, I got two binomials that I'm multiplying together. FOIL. So I have 1/2 mass times V final dot V final. Plus V final dot V initial minus V initial dot V final minus V initial dot V initial.
What, incarnation?
Did you just,
Foil. Yep. I assume the word, when I say foil, everyone's in sync with it, or? Okay.
I have a question for you. I just wanna make sure, so between the M of the displacement over time, that equation, and the one below it. Yeah, so that equation, and then the one below it, so between there, you just, because you got the VF minus VI
Right.
twice, you just put it in for the displacement, right?
I saw,
You just,
this
yes,
is the displacement.
yes.
Yeah.
And you just substituted it in.
And then here,
At the
and then delta V, change in anything is always final minus initial, so that's where that comes from.
Okay,
But delta T's canceled,
yeah, that's what,
1/2 came out.
okay.
is there an easier way instead of just writing all those V's out? I know you would have numbers in the real equation. Is that what you just have to do?
No, Jim, you have to.
Well, we're getting to hopefully a simpler, at least, we're getting to definitely a simpler looking form. But physics sometimes has what's one professor referred to as conservation of complexity. The fewer letters there are, the more that gets thrown into every letter. We will simplify this, because, matter of fact, some of that cancels out. Because remember, commutative property holds, it doesn't matter the order in which you do a dot product, so those add up to 0. Or cancel each other out, however you want to word it. That minus that is 0. So now I'm left with VF dot VF and VI dot VI. So let's think about a dot product of a vector with itself. It should be the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. And what is the angle between a vector and itself?
0.
Doesn't matter if you're talking radians or degrees. And so what you end up with is just the magnitude squared. So